Welcome to Talk Tensors.
It's great to be here for another deep dive.
Yeah, and I want you, the listener, to start off today by picturing something. Just imagine you're playing a classic video game.
Like Super Mario.
Exactly like Super Mario. So you're running through a level, right? And your character jumps up, hits a block, and absorbs a fire flower.
And now you can throw fireballs.
Right. But then a few moments later, you find a super leaf.
Oh, nice. Now you can fly.
Exactly. So you're absorbing these distinct, specialized items, and your character just stacks these abilities completely seamlessly.
Yeah, you become this ultimate multi-powered entity.
Right. You're utilizing all these different skills at the exact same time without, one canceling out the other.
It's just layer upon layer of abilities.
Yeah. Now, what if I told you that we could do exactly this, but with artificial intelligence?
I mean, honestly, it sounds completely like science fiction.
Right.
Or at least, something that would require a supercomputer the size of a city block to actually calculate.
Yeah, that's what you would think.
But what is so fascinating about the technology we are unpacking today is that this isn't some hypothetical scenario.
Yeah.
It is a very real, very current breakthrough in how we handle machine learning architectures.
And that is exactly the subject of today's deep dive. We are looking at a viral trending technique in machine learning that basically allows us to take multiple highly specialized language models.
Think of one model as an absolute math whiz, maybe.
Yeah, exactly. One is a math whiz, another model is an expert senior coder, and maybe a third is like a highly empathetic general conversationalist.
And we just merge them.
Right, we merge them into one ultimate Super Mario model. And the absolute kicker here, the thing that has the entire tech community just reeling, is that this process requires absolutely no retraining.
Not at all.
It requires no extra data. It doesn't even require a single GPU to pull off.
Which is wild.
Right, you can do this entire merging process on standard, everyday CPUs.
Which completely democratizes the entire development pipeline. I mean, it's a fundamental paradigm shift away from the idea that only, mega corporations with billion-dollar compute budgets can build state-of-the-art multidisciplinary AI systems.
So here is our mission for this deep dive. We are going to deconstruct this trending technique, which is called DARE.
DARE.
Right. That stands for drop and rescale. We're going to explore its highly counterintuitive architecture, and we're going to look at why it completely upends our fundamental understanding of what actually happens when an AI learns a new skill.
Because it really challenges a lot of core assumptions.
It really does. And we're also going to look at the real-world performance metrics, because this isn't just an academic theory, right?
No, not at all.
This technique actually pushed a relatively small 7 billion parameter model to the absolute top of the Open LLM leaderboard.
Beating out models backed by massive corporate funding, I might add.
Exactly. So we're going to figure out what this means for the future of open source AI. I look at this entirely as like a cheat code for machine learning practitioners.
It certainly functions exactly like a cheat code. And if we connect this to the bigger picture, the overarching thesis we are going to explore today is this.
Let's hear it.
The DARE technique works because it aggressively exploits the extreme redundancy inherent in neural networks.
Redundancy. Okay.
Yeah. It essentially proves that fine-tuning a model to do a specific task is far less about learning new things and much more about unlocking what is already there.
Unlocking what's already there. I love that. Okay, before we can understand how to merge these giant artificial brains together, we really need to understand what happens when we upgrade them in the first place.
Right, the fine-tuning process.
Yeah. When someone says a model has been fine-tuned, what is physically happening inside that black box? Let's start from this. We have a pre-trained model, right? Something massive, like Llama 2.
Yeah, to set the stage for you, the listener, the pre-training phase is where the model essentially reads the internet.
Just absorbs everything.
Right. It is exposed to trillions of words. During this phase, it learns grammar, it learns facts, it learns reasoning, and it learns the very structure of human language.
And this takes a huge amount of computing power, right?
Oh, absolutely.
Yeah.
This process takes thousands of GPUs running continuously for months, and it costs millions of dollars. But, and this is crucial, a base pre-trained model is fundamentally just a text predictor.
Right. It just wants to finish a sequence of words.
Exactly. If you ask a base model a question like, what is the capital of France?
It might not just say Paris.
Right. It might not give you the answer at all. It might just generate another question like, what is the capital of Germany? Because it thinks you're writing a quiz.
Because it's seen a million quizzes on the internet.
Exactly. So to make it actually useful, to make it follow instructions or solve specific mathematical word problems, we have to perform what is called supervised fine-tuning, or SFT.
SFT. So during SFT, we sit the model down and give it highly specific examples of the behavior we want.
We guide it.
Right. We say, here is a complex math problem, and here is the exact step-by-step logical solution.
Right.
And as it trains on these, tens of thousands of specific examples, its internal weights, its billions of parameters, start to change and shift slightly to accommodate this new behavior.
And this brings us to the core conceptual building block of our entire discussion today.
Which is?
The delta parameter.
The delta parameter. Okay.
Imagine you take the massive, multi-dimensional spreadsheet of numbers that makes up the original pre-trained base model.
Got it. Big spreadsheet.
Then you take the spreadsheet of the new fine-tuned math model.
Okay.
If you mathematically subtract the base model from the fine-tuned model, the difference that is left over is the delta.
Oh, okay. So it's just the exact changes.
Exactly. It is the pure mathematical representation of what changed during that fine-tuning process.
I was looking at the actual numbers behind this delta shift, and it completely broke my intuition about how these systems operate.
The scale of it is pretty shocking.
Yeah. The physical reality of these delta parameters is shockingly minuscule. The specific SFT delta parameter values typically stay within a range of just 0.002.
It's tiny.
We are talking about microscopic fractional modifications to this massive pre-trained brain.
It is a phenomenal observation, and it really highlights a major misconception about AI.
How so?
Well, you have this foundational model, say 13 billion parameters, and to turn it from a babbling general text generator into a highly specialized, laser-focused mathematical reasoner.
Because think you'd have to rewire the whole thing.
Right, but you aren't. You are barely nudging the dials. The absolute values of these changes are frequently less than 2/1000ths of a point.
I was trying to visualize the scale for you, the listener. Imagine the pre-trained model as this massive, incredibly complex soup that has been simmering in a giant industrial vat for months.
Okay, I like soup.
Right. It has millions of raw ingredients, deep, complex flavors representing, the entire internet. Now, the SFT delta parameters, the fine-tuning process, it isn't throwing a whole new vegetable into the vat.
It's not a whole new ingredient.
No, it isn't a new cut of meat. It's just a tiny, almost invisible pinch of a highly specific spice.
Just a little seasoning.
Yeah, like a fraction of a gram of cumin to transform the entire vat into a math soup.
Yeah.
Or a hint of basil to make it a coding soup.
That's a great way to put it.
But here's the part I really need you to explain to me.
Okay.
If the changes are so infinitesimally small, literally just a tiny pinch of spice, why do they so radically change the model's behavior? How does a shift of 0.002 turn a generalized text predictor into a master programmer?
This cuts right to the heart of how neural networks actually store capabilities.
Yeah.
And it introduces the concept of overparameterization.
Overparameterization?
Right. While SFT unlocks specific capabilities, it does so with extreme, almost wasteful redundancy.
Redundancy again.
Yes. When the model is running through gradient descent, which is the algorithm it uses to optimize its parameters and learn that specific math task, it doesn't just cleanly adjust one tiny, efficient, logical circuit in its brain.
It doesn't just build a math module.
No. It spreads that tiny mathematical adjustment across billions of parameters. It acts like a massive echo chamber.
Wow.
The vast majority of those tiny delta parameters aren't actually carrying critical, unique new information. They are simply redundant echoes of the fine-tuning process.
So wait, we are changing billions of knobs just a tiny fraction of a millimeter when mathematically we maybe only needed to turn a handful of knobs a full rotation? We are smearing the learning across the whole network.
Exactly. The model updates broadly across its entire architecture because that is simply how the mathematical optimization of gradient descent functions.
It just looks for the easiest path.
Right. It looks for the path of least resistance across the whole network.
Yeah.
It does not update broadly because every single one of those billions of updated parameters is structurally necessary to perform the new math skill.
Okay, if I am following this logic, if these delta parameters are mostly just redundant filler, right, just echoes of the actual learning signal smeared across billions of connections, what happens if we just go in and delete them?
And that precise, slightly terrifying question leads us directly to the core innovation of this deep dive.
Let's get into the DARE mechanism itself. Drop and rescale. This is the absolute meat of the technique, and it involves two steps that feel like they, break the laws of physics, or at least the laws of computer science.
It definitely feels wrong the first time you read it.
It does. Let's start with the first step, the drop. You take this highly specialized, fine-tuned model, you isolate that delta parameter spreadsheet we just talked about, and you drop a massive percentage of them.
You literally set their value to absolute zero.
You delete the fine-tuning.
You are mathematically erasing the very changes that cost you time and money, the changes that made the model a specialist in the first place.
It's crazy.
And the percentage of parameters they are dropping is not trivial. We aren't talking about trimming 5 or 10% of the fat to optimize the model.
No, the numbers are staggering. If you have a 70 billion parameter model, something massive like WizardMath 70B, which is a highly respected mathematical model, you can drop up to 99% of its delta parameters.
99%.
For the slightly smaller but still massive 7 billion or 13 billion parameter models, you can safely drop 90% of the deltas. I really want you, the listener, to let that sink in for a moment.
It's hard to believe.
Someone spent immense compute power fine-tuning a model on complex equations, and you can just zero out 90 to 99% of the exact mathematical changes they made, throwing them in the digital trash.
If you read that completely out of context, you would assume the model is permanently broken. You are giving the AI localized amnesia.
Hold on, I have to stop you there because I know exactly what the listener's thinking right now. This defies common sense. If I just spent all this time giving this AI a highly specific instruction manual on how to write Python code, and now you want me to literally rip out and burn 90% of the pages in that manual,
Right.
How does the AI not just completely forget how to code? Think about a massive choir.
That's wire, okay.
Let's say I have a choir of 100 people singing a very specific, beautiful, complex harmony.
Sure.
If 90% of the singers just stop singing, if I zero them out and tell 90 people to leave the stage, the song disappears. It's just 10 lonely people whispering. The harmony is fundamentally gone.
That is an incredibly useful visual, and it perfectly sets up the second crucial half of the DARE technique.
The rescale step.
Exactly, the rescale step. Yes, 90% of your choir has just gone completely quiet.
Right.
The volume and the overall impact of the song have plummeted. But what do you do with the 10% of the singers that are left on the stage?
What do?
You hand them megaphones.
Oh, wow. So we amplify the survivors to compensate for the missing.
Exactly. Let's look at the actual math of it, because it is wonderfully elegant.
Let's hear it.
If you drop a certain percentage of parameters, let's call that percentage P, you must rescale the surviving parameters by multiplying them by a specific factor.
Okay, what's the factor?
The factor is 1 divided by 1 minus P.
1 over 1 minus P.
Right. So if you drop 90% of the parameters, your P is 0.9.
Okay.
1 minus 0.9 leaves you with 0.1.
That checks out.
1 divided by 0.1 equals exactly 10.
Yeah.
Therefore, you multiply the raw value of the remaining 10% of the delta parameters by 10.
You literally turn the volume dial up to 10 on the surviving data points.
You do. And the reason this works isn't just some clever programming hack. It is deeply grounded in the fundamental mathematics of how neural networks process information layer by layer.
Right.
Neural networks rely incredibly heavily on linear transformations. At its core, a neural network is just multiplying inputs by weights and adding biases over and over again.
Just massive matrices doing math.
Exactly. The researchers behind DARE proved mathematically that by applying this specific rescale factor, the expected value of those linear transformations remains virtually identical to what it was before you deleted 90% of the network.
Let's slow down and define some of these terms because this is the magic trick of the whole episode.
Good idea.
We need to talk about embeddings and expected value to make sure we are all visualizing the exact same thing here.
Let's break it down. Embeddings are the internal mathematical representations of the data as it flows through the various layers of the neural network.
So it's how the AI actually sees a word.
Right. When you type a word into an AI, it doesn't see letters. It sees a coordinate in a massive multidimensional space. That coordinate is the embedding.
Okay.
And as that data moves from layer 1 to layer 2 to layer 3 of the neural network, those coordinates are shifted and transformed by the weights.
So the goal is to make sure that the coordinate coming out of layer 1 looks exactly the same to layer 2, regardless of whether you are using the full massive set of delta parameters or our new hollowed out sparsified DARE version.
Exactly. And this is where the concept of mathematical expectation comes in.
The expected value.
Right. The expectation is essentially the statistical average output of that layer. Because we randomly dropped 90% of the parameters, we reduced the overall signal by 90%.
The choir got quiet.
Right. But by multiplying the remaining 10% by 10, the mathematical average of the output, the expectation, remains entirely constant.
That's brilliant.
Layer 2 of the neural network receives the data and doesn't even realize that 90% of layer 1's parameters have been zeroed out.
Because the overall signal strength, the volume, and the general direction of the embedding are perfectly preserved.
Exactly.
That is wild. The embeddings still look the same to the AI. The ghost of the full choir is still present in the room because the remaining 10 singers with megaphones are projecting the exact same overall frequency, shape, and volume.
The harmony survives.
The harmony survives. And here's where it gets incredibly interesting regarding the future of AI. If we connect this DARE mechanism to scaling laws.
Oh, this is a fascinating part of the paper.
Yeah, the data shows that the larger the foundation model is, the higher the drop rate it can tolerate.
Right.
A 7 billion parameter model starts to degrade and lose its abilities if you drop more than 90%. But a massive 70 billion parameter model handles a 99% drop without breaking a sweat. Its performance stays completely stable.
Which is a profound, almost philosophical insight into how these giant models operate.
How so?
It strongly suggests that as we scale models up, as we pour more money into adding billions of parameters to the base model, the redundancy during fine-tuning scales up even faster than their capability.
Wow.
A 70 billion parameter model is so incredibly over-parameterized for the simple task of fine-tuning that 99% of the mathematical updates it makes are functionally irrelevant filler.
As long as you rescale.
Right, provided you just boost the volume on the remaining 1% that randomly survived.
It paints a funny picture. It's like a massive corporate bureaucracy where 99% of the middle managers are just forwarding emails back and forth, contributing absolutely nothing to the actual product.
I can see it.
And if you fire 99% of them and just give the remaining 1% a much stronger cup of coffee to work faster, the company's output remains exactly the same.
It is a slightly cynical way to view corporate structure, perhaps, but mathematically, it is an incredibly accurate representation of gradient descent in large language models.
Okay, but proving the math works in a theoretical sandbox is one thing. How do we know the rescaling step, the megaphones, is actually the secret sauce?
We have to test it.
Right. How do we know it isn't just that the 70B model is so physically robust and massive that it can survive massive brain damage regardless of what we do? Let's look at the control experiments they ran to prove this. Why do alternative, seemingly more logical methods fail?
This is where we get into the ablation studies.
Ablation studies.
Yeah, and in scientific research, an ablation study is where you selectively remove parts of your system to see what breaks,
Right.
which tells you what was actually important.
You take it apart piece by piece.
Exactly. The researchers tested a baseline method they called drop-only. This is exactly what it sounds like. You drop the 90% of parameters, but you do not apply the rescale factor.
No megaphones.
No megaphones. You don't give the megaphones to the surviving choir members. You just zero out the weights and walk away.
And what happens to the AI?
It catastrophically crashes.
I figured.
To measure this, they looked at the cosine similarity of the model's embeddings.
Let's unpack cosine similarity for a moment because it's a brilliant way to measure AI brain activity.
Go for it.
If an AI sees a concept as a vector-like, an arrow pointing in a specific direction in a high-dimensional space cosine similarity measures the angle between two different arrows. If you have the original model's arrow and the newly damaged model's arrow, a cosine similarity score of 1.0 means they are perfectly aligned, pointing in the exact same direction. They're having the exact same thought.
That's a perfect explanation. Now, let's look at the drop-only numbers.
Hit me.
On the WizardMath 7B model, if you drop just 50% of the delta parameters without rescaling them, the cosine similarity drops down to 0.85.
Oh, wow.
The vector is drifting. The AI's thoughts are becoming misaligned. If you drop 90% without rescaling, the similarity crashes to 0.68.
That's a huge drop.
The internal representations are completely distorted. The arrows are pointing in entirely different directions. The next layer of the neural network receives absolute garbage data.
And the performance?
Consequently, the model's ability to actually solve math problems on benchmarks like GSMA-K just plummets to near zero.
So the rescale, the mathematical compensation is absolutely vital. The megaphones are load-bearing.
Extremely load-bearing.
But here's another question I had when I was wrapping my head around this. What about being smart about what we choose to drop?
Picking and choosing.
Yeah. The DARE method uses purely random dropping. It is a Bernoulli trial. For every single parameter in that spreadsheet, it is essentially spinning a roulette wheel or flipping a heavily weighted coin to decide if that parameter lives or dies.
It doesn't look at the value at all.
Right. It just deletes blindly. But historically in machine learning, we have traditional pruning techniques like magnitude-based pruning or MP.
Yes, very common.
With MP, you don't drop randomly. You carefully look at all the parameters and you selectively delete only the absolute smallest values, working under the logical assumption that the tiny numbers are the least important, and you preserve the large numbers.
Which intuitively makes perfect sense to human logic. You trim the weakest branches from the tree to save the strong ones.
Exactly.
But the hard data reveals that magnitude pruning actually performs significantly worse than Dare's completely blind random dropping.
I really want to linger on this because it is deeply counterintuitive. Why is deleting parameters completely randomly, like a tornado tearing through the model, actually better for preserving intelligence than thoughtfully and analytically deleting the weakest parameters?
It remains counterintuitive until you apply a critical systemic lens to what a delta parameter actually represents in this specific context.
Okay.
SFT delta parameters are not like traditional base pre-trained weights, where the absolute size of the number directly correlates to its structural importance.
Oh, right, because they're all tiny anyway.
Remember our earlier point. All the deltas are incredibly tiny to begin with. They are mostly under 0.002. They don't represent giant load-bearing pillars of knowledge.
So what do they represent?
They represent an aggregate, highly distributed, subtle shift in the model's overall behavior. Even the absolute tiniest, most microscopic deltas are contributing a vital frequency to the overall mathematical expectation of that layer.
So if you use magnitude pruning and you methodically delete all the smallest numbers, you aren't just trimming fat. You are systematically silencing a specific frequency in the choir. You are taking out all the sopranos or all the baritones.
Precisely. You are intentionally skewing the distribution of the data.
Wow.
By throwing away only the tiny parameters and hoarding the relatively larger ones, magnitude pruning completely fails to preserve the original mathematical expectation of the embeddings.
It shifts the arrow.
It artificially shifts the entire vector in one direction. Random dropping, on the other hand, acts uniformly. Because it is a uniform random distribution, it perfectly preserves the overall shape and distribution of the weights.
It drops large and small deltas equally.
Yes. Combined with the targeted rescaling factor, uniform random dropping is the only mathematical way to perfectly mimic the ghost of the full massive delta parameter set.
Okay, this is all incredibly elegant math, but now we have this tool, DARE. We have proven we can safely hollow out 90% of a model's fine-tuned weight adjustments without losing its specialized abilities. We are left with these massive, mostly empty delta matrices spreadsheets filled with 90% zeros. What incredible trick does this actually unlock for practitioners? Like, why are we going through all this trouble to empty out the model?
And this brings us to the absolute payoff of the technique. We are entering the realm of model merging, which creates what you referred to earlier as the Super Mario effect.
This is where the magic trick happens. Imagine you want to build the ultimate AI assistant. You start by taking 3 entirely different open source models.
Okay.
Let's say they are all fine-tuned from the exact same base foundation, like Llama 2. You have a model called WizardLM, which has been fine-tuned extensively to be great at chatting, empathy, and following general instructions.
A good conversationalist.
Yeah. Then you have WizardMath, which is fine-tuned purely on complex math datasets and logical reasoning.
The math whiz.
Right. And third, you have Code Alpaca, which is fine-tuned to be an expert at writing Python and C++ out.
The coder.
Exactly. You are a developer, and you want a single model that does all 3 of those things perfectly.
Traditionally, if you want a model that can chat, do math, and code, you have 2 very painful options.
Let's hear the painful options.
Option 1. You build a massive, complex, curated dataset containing chat logs, math problems, and code repositories. And you spend hundreds of thousands of dollars renting a GPU cluster to do multitask training from scratch.
Very expensive. Very hard.
Option 2. You try to mathematically merge the weights of the 3 existing open source models.
Okay.
There are techniques that have existed for a while to do this, like task arithmetic or ties merging, where you basically try to mathematically average the parameters together.
But there is a massive roadblock with traditional merging. Normally, if you just mathematically average the densely packed weights of these three models, they step on each other's toes.
You do.
Let's visualize that matrix spreadsheet again. If at layer 12, neuron 45, the math model made a plus 0.002 adjustment, but the code model made a minus 0.0002 adjustment, and you add them together.
They cancel each other out to zero.
Exactly. The math logic interferes with the coding logic. The text generation gets muddied and confused. The researchers call this parameter interference.
It is the fundamental bottleneck of model merging.
Right.
If every single model has slightly adjusted all of its billions of parameters to serve its specific task, mixing them together creates a muddy, diluted, incoherent signal.
The AI just gets confused.
The AI essentially becomes schizophrenic.
But now we introduce DARE to the equation. Because you have gone in and zeroed out 90% of each individual model's delta parameters, they no longer collide.
You have completely neutralized the interference problem. By applying DARE, you have sparsified the updates.
Sparsified.
Made them sparse.
Exactly. You have turned them from dense, overlapping, highly populated matrices into highly sparse matrices that are 90% empty space.
Oh, I see where this is going. Because they are mostly zeros, they now fit together like puzzle pieces. When you use task arithmetic to add the sparsified math deltas, the sparsified code deltas, and the sparsified chat deltas together, the actual non-zero numbers rarely occupy the exact same parameter slot.
So they don't cancel each other out.
Right. The mathematical collision rate drops exponentially.
But let's picture it like this. Imagine placing 3 different dense text documents printed on transparent paper and stacking them directly over each other.
Oh, that's a good visual.
Normally, because every page is full of dense black text, when you stack them, it's just a black, unreadable, overlapping mess. That is parameter interference.
Right.
But DARE comes in and acts like an eraser. It randomly erases 90% of the ink on each individual document. It leaves just enough structure rescale to be bold so that the meaning is preserved.
The megaphone.
Exactly. Now, when you stack those 3 newly sparse transparent pages on top of each other, the text rarely overlaps. You can look through the stack and read the code, the math, and the conversation perfectly.
It is an excellent visual representation of sparse matrix addition. And when we look at the real-world performance of this merged Super Mario model, the results are staggering.
Tell me about the results.
The researchers took those 3 exact models, LM, math, and code sparsified them with DARE, and merged them using task arithmetic. The results didn't just preserve the individual abilities of the models, the merging process actually improved them.
When I first saw these results, I thought it had to be a typo. Let's look at the actual benchmarks. On the MBPP coding benchmark, which tests pure programming ability, the merged Super Mario model jumped 19.57% compared to the standalone dedicated code model.
19.57%.
On the GSM-8K math benchmark, it improved by 3.18% over the standalone math model. On Alpaca, which tests general instruction following in chat, it improved by 3.10%.
We truly have to pause and note the historical and architectural significance of what those numbers mean. The aggressively merged model actually surpasses the performance of the individual specialized source models on their own dedicated tasks.
The models are essentially cross-pollinating.
Right.
The strict step-by-step logic learned by the math model is somehow bleeding over and helping the coding model write cleaner, more logical Python. And the empathetic conversational skills of the language model are bleeding over and helping the math model explain its steps in a more readable way.
Exactly.
And they achieve this deep synergy without a single second of further training.
And we cannot emphasize this point heavily enough for the practitioners listening. This entire DARE sparsification and task arithmetic merging process was done on a standard CPU.
It's unbelievable.
This fundamentally democratizes advanced AI development. You do not need to rent a massive A100 GPU cluster to build state-of-the-art multimodal AI anymore.
Anyone can do it.
You can literally download the open source specialists from a repository, run a lightweight Python script to drop and rescale the matrices on your local laptop, merge them together via simple addition, and you have your own custom synergistic Super Mario model.
Which brings us to the ultimate proving ground, the Open LLM leaderboard. To prove this wasn't just some isolated academic exercise that only works in a lab, the researchers applied DARE to the Wild West of open source 7 billion parameter models.
They grabbed models that were already highly ranked by the community, sparsified them, and merged them together.
Right. They created merged models they dubbed Super Mario V1 and Super Mario V2.
And the result of that experiment was a complete validation of the technique. By fusing heavily optimized models like Neural Beagle and Turtis, and then bringing in West Severus and Wild Macaroni, all using this exact drop and rescale sparse merging technique, Super Mario V2 achieved the absolute #1 rank on the Open LLM leaderboard as of January 28, 2024.
The #1 rank.
A merged, CPU-generated model beat out natively trained, highly complex, wildly expensive models from major tech labs.
It feels like the ultimate free lunch in computer science.
It really does.
But, as with any cheat code or exploit in a video game, there are strict boundaries. There are failure modes. You can't just apply DARE to any model you find on the internet and expect magic to happen.
No, you definitely cannot.
So we need to look closely at the boundaries of this technique. When does DARE completely break the game? And more importantly, what do those failures teach us about how AI actually learns?
The underlying research is very transparent about where DARE fails. And the mechanics of those failure modes are incredibly instructive for understanding neural architectures.
Okay, lay them out for us.
There are two primary conditions where applying DARE will completely crash the model. Failure mode 1 is when the delta parameters far exceed that microscopic 0.002 threshold we discussed earlier.
Okay.
And failure mode 2 is when you attempt to drop fine-tuned parameters as a whole instead of isolating just the delta parameters.
Let's unpack that first one because it reveals a massive difference in training methods. They document a failure case involving a model called WizardCoder Python 13b.
A very capable model.
Yeah. The authors tried to apply DARE to this highly respected coding model, and they used Llama 213b as the base. But when they applied the drop and rescale, the pass rate on coding benchmarks dropped to a flat, absolute zero.
Zero.
The model was lobotomized. Why did it break so spectacular?
It broke because of how WizardCoder Python was originally built. It wasn't just fine-tuned via SFT on a few thousand coding examples like the other models we discussed.
Okay.
The base model it was built from, which was Code Llama, had undergone a massive, resource-intensive process called continuous pre-training. Before it was ever fine-tuned, it was fed an additional 500 billion tokens of pure code data.
Ah, I see. So returning to our soup analogy, continuous pre-training wasn't just adding a tiny pinch of spice to the vat. They poured an entirely new, massive vat of code broth into the original soup and boiled it down again.
That is exactly the distinction. When a model undergoes continuous pre-training on hundreds of billions of tokens, it is not just shifting its behavior, it is fundamentally rewiring its base knowledge and its deep structural pathways.
Wow.
Because of this massive influx of deep data, the delta values, the mathematical difference between the original Llama 2 and this deeply trained coding model, has swelled enormously. They are hovering around 0.03.
Which is more than an order of magnitude larger than the 0.0002 deltas DARE is designed for.
Right. And that size matters immensely. The entire DARE technique relies on the changes being microscopic and highly, highly redundant.
Right.
Once the mathematical changes become that large, they are no longer redundant echoes. They are structurally significant, load-bearing pillars of new knowledge.
So dropping 90% of them?
If you drop 90% of a structurally significant network, you are destroying the actual learned representations, and no amount of megaphone rescaling can save it because the foundational geometry is gone.
It's just broken.
Exactly.
Yeah.
DARE only works on the superficial layer of supervised fine-tuning. It does not work on deep, continuous pre-training.
Okay, that makes perfect logical sense. SFT is about alignment and formatting. Continuous pre-training is deep knowledge injection. Now, let's look at the second failure mode, because this is the one that really gives us that massive aha moment regarding AI philosophy. The fine-tuned parameter drop experiment.
To understand this failure, we have to look at the exact variables we are manipulating. In all the successful DARE experiments we've discussed, we isolate the delta.
Right, just the tiny mathematical difference made during the SFT process.
Yes, and we drop 90% of those specific delta numbers. The massive underlying matrix of the pre-trained base model weights is left completely untouched and pristine.
The big vat of soup stays the same.
Right. But the researchers asked a vital question. What if we don't isolate the delta? What if we just take the final fine-tuned model in its totality, the base weights plus the delta weights all mixed together, and apply random dropping to that total sum?
The results of that experiment are shocking. If you try to drop the total parameters, dropping even a tiny fraction causes the model's capabilities to catastrophically fail.
It's brutal.
On the Alpaca benchmark, dropping just 10% of the total fine-tuned parameters caused the AI's score to plummet from a highly capable 67-point VUO all the way down to a useless 8.56. The model effectively dies from a 10% drop.
It's an incredibly striking contrast. You can drop 90% of the delta, but you can't survive a 10% drop of the total.
I really want you to unpack the philosophical and architectural meaning of this for us.
Sure.
If I can delete 90% of the new learning, the fine-tuning delta, and the model is perfectly fine, maybe even better, but the model completely dies and loses all coherence if I delete just 10% of its total combined brain. What does that empirically prove about how artificial intelligence actually learns during the fine-tuning stage?
This is the critical foundational insight for you, the listener, today. It empirically proves that supervised fine-tuning does not actually teach the model new fundamental capabilities.
Really? It doesn't teach it?
No. The pre-trained foundation model, the base Llama 2 that read the internet, already knows how to do complex math. It already knows how to write Python code. It already knows how to chat empathetically.
Because it read it all during pre-training.
Yes. The knowledge is fully latent within it. The SFT process merely acts as a key that unlocks, formats, and aligns those pre-existing abilities so we can access them predictably.
So the billions of dollars spent pre-training the base model on massive GPU clusters, that is where the actual heavy lifting intelligence is built and stored. The fine-tuning process, which we obsess over, is just superficial formatting. It's just giving the AI a user interface.
That is the reality. DARE proves mathematically that this SFT key is incredibly wastefully redundant. It's a massive, overly complex key spread out over billions of parameters, but you only need a tiny, sparse 10% fraction of it to successfully turn the lock.
Wow.
However, the lock itself, the deep pre-trained base weights, is deeply structural and highly load-bearing. If you randomly delete 10% of the lock, the whole door falls off its hinges and the system collapses.
That is an amazing analogy.
The knowledge is inherent in the pre-trained model.
No.
SFT is just pointing a flashlight at the right part of the brain.
That completely shifts my entire mental model of how we interact with these systems. We aren't training them to be smart during fine-tuning. We are simply teaching a very smart, very chaotic entity how we want it to behave.
Exactly.
Understanding this fundamental truth about how models still are knowledge leads us to look at the horizon. With this new understanding of sparse keys and structural locks, what comes next?
We have to look at the immediate practical implications first, because they are actively changing the industry right now. For the developers and practitioners listening, this completely upends the economics of AI development.
Yes, let's summarize exactly why you, the listener, should care about this going into the future. This breakthrough means you no longer need a massive compute budget to build state-of-the-art, highly specialized multi-tool models.
No budget needed.
You do not need to rent time on an A100 GPU cluster. You can go to an open source platform like Hugging Face, download highly specialized models that fit your specific industry. Maybe you grab a medical diagnostic model, a legal contract analysis model, and a robust coding model. Run them through a lightweight DARE script on your standard laptop CPU and merge them.
Right on your laptop.
You can create a bespoke, synergistic Super Mario model tailored to your exact personal workflow entirely for free.
You're effectively bypassing the traditional massive bottleneck of AI development, which is compute cost. You are leveraging the millions of dollars that big tech companies have already spent on pre-training and initial fine-tuning, extracting the sparse keys, and mathematically combining their outputs without paying the tax of parameter interference.
It is incredibly empowering. Now it is time for my absolute favorite part of the deep dive, the novel notions segment.
I always look forward to seeing where you take these concepts.
Please note, for everyone listening, the following novel notions segment is highly speculative. It is a thought experiment meant for entertainment purposes only, though it is deeply grounded in the math we've discussed today.
Disclaimer noted. Let's hear it.
I want to pitch you an outlandish but completely plausible scenario based on the DARE paper. I call it the global neural BitTorrent scenario.
Okay, lay out the architecture for me.
Because DARE definitively proves that a model's task-specific alignment is just a highly sparse, easily extractable delta layer, and because we know we can safely delete 90% of it and just use the rescale 10%, what if the future of AI isn't downloading giant, monolithic 70-gigabyte model weights every time there's a minor update?
Okay, so what are we downloading?
What if we see a decentralized peer-to-peer ecosystem emerge, a true BitTorrent protocol, but for AI microskills?
So instead of sharing massive full-weight models that take hours to download, users are only sharing these tiny sparsified DARE deltas.
Exactly. Imagine millions of users worldwide locally fine-tuning their base models on highly specific, incredibly niche micro tasks. Let's say a lawyer in Austin fine-tunes a model just to write legal briefs in accordance with the state of Texas.
Sure.
A programmer in Tokyo fine-tunes one just to optimize an obscure legacy coding language. A doctor in London fine-tunes one on the absolute latest pediatric research papers.
All incredibly useful specific tasks.
They perform their SFT, they extract the delta, they run DARE to drop 90% of it, and what is left is a microscopic file. We're talking about a few megabytes. They upload that sparse DARE delta to a decentralized global network.
If we map out the probability of this, the technical mechanism to support it is already fully validated by the research we've discussed. A user's local base model could be configured with a script to automatically connect to this decentralized network.
Yes.
Overnight, while you are sleeping, your computer downloads thousands of these tiny, highly verified, extremely sparse skill deltas from peers around the globe.
Yeah. And because DARE makes these matrices so sparse, it eliminates the parameter interference problem. So your computer simply uses task arithmetic to mathematically add all thousands of these microskills directly into your local model's active memory using nothing but your CPU.
The implications of that are staggering. Your personal AI would literally absorb the specific, highly specialized, up-to-the-minute skills of the global community while you sleep.
Like waking up in the Matrix and saying, I know Kung Fu.
Right. You wake up the next morning and your local model suddenly knows the nuances of Texas law. It can code in obscure legacy languages. It knows the diagnostic criteria published yesterday in London. It creates a constantly evolving, crowdsourced hive mind model with virtually zero centralized compute cost or bottleneck for the end user.
It would be a truly open source intelligence that grows every single day, patched together by millions of microscopic DARE deltas. It is the ultimate realization of the Super Mario analogy, absorbing millions of specialized power-ups from around the world without ever slowing down.
It is a genuinely fascinating and technically feasible scenario for the future of distributed AI. But contemplating that future also leaves us with one final, deeply provocative thought. Something for you, the listener, to mull over as we wrap up today's deep dive.
Bet on us.
We'd have spent this entire time marveling at the fact that we can delete 90 to 99% of a model's fine-tuning. But let's look at the dark side of that math.
The dark side. Okay.
If 99% of the mathematical adjustments we force an artificial intelligence to make during fine-tuning are fundamentally useless noise, just mathematical echoes we can randomly delete with zero loss in actual capability, what does that tell us about the crude efficiency of our current training algorithms?
Wow. That flips the whole achievement on its head.
Exactly. Are we as an industry currently spending hundreds of millions of dollars on electricity and massive GPU compute clusters just to brute force a 99% redundant key?
It's a huge waste of energy.
It is. The sheer success of the DARE technique strongly suggests that our current optimization methods, like gradient descent, are incredibly blunt, inefficient instruments.
Yeah.
The next trillion-dollar AI breakthrough won't necessarily be the company that figures out how to build a bigger model with more parameters. It'll be the company that figures out the math to only train the 1% that actually matters from the very beginning, bypassing the 99% waste entirely.
So until we figure out the math to build the lock without forging the massive redundant key, keep absorbing those power-ups and keep sparsifying your models. Thank you for joining the conversation today. We will see you on the next deep dive.